All right. I think we can start now. Okay. So yes, on Thursday we discussed uh, concepts from week 1 to week 4. Today we are going to discuss the remaining concepts of linear algebra that you guys studied in this term. So we will start with null space of the matrix. Okay. So can anyone recall what is the null space of a matrix quickly? Given a matrix of m cross n, order m cross n, what is a null space of the matrix? Given m cross n matrix of order m cross n, what is the nullity? So null space of A is defined as,
Sir, all those points that gets cancelled.
correct. So set of all x inside your vector space, or in this case it is in Rn at x over Rn, such that Ax is equal to a 0 value. All right. So this is the definition of the null space. On the right hand side, I have mentioned the definition. So quick examples of null spaces. If you have null space of identity matrix where the diagonal entries are 1, rest of the entries are 0, what is the null space of a identity? So, now that, yeah, null space of the identity matrix. What will be the null space of this matrix?
It will be a singleton set considering only zero matrix.
Correct. So it will be just a vector 0, 0, 0 n many times. And in case of suppose you have a scalar matrix, then what would be the null space? If you have a scalar matrix, let's say of 2 cross 2 order, then what would be the null space? Assuming that k is non-zero.
0, sir.
Yeah, it would again be a 0 vector. All right. Okay, so here is a question on the left hand side where you need to find out the null space of matrix 4 cross 3. Okay, so what is the correct option? First, you have given a subspace W, set of all vectors in R4 such that Ax equal to 0 of R4. Second option, you can see all the options. Now, what would be the null space of matrix 4 cross 3?
It will be the second one because its order will be 3, right? R3.
Yeah, so this matrix will be acting on or will be applied on vectors that sits inside R3. Correct? So the option 3 will be, this option 2 will be correct. All right, good. So now let's, so what is the nullity of a matrix? The nullity of a matrix is defined to be nullity of a matrix is defined to be the dimension of the null space of matrix A. All right. So in the example of the identity matrix and of the scalar matrix, the null spaces, we have found out it is going to be just a single vector. Now, what is the nullity in each of the cases?
1, sir.
It's 0.
1.
Sorry, sir.
Is it-
0. 0, sir.
Yeah, it is 0 because it is single term. Okay. So the nullity in our example is 0. Okay. Okay. So now let's recall these two concepts by solving this problem, which is given on the left hand side. Okay. So let us first also recall that what is a nullity? Nullity is nothing but the number of independent variables that you get in the RREF form. Okay. So it's the number of independent variable of A. All right. So nullity of A is equal to the number of independent variables of A, which is also equal to the yeah, that is what it is. Well, and how to find out the independent variables. So in order to find out independent variables, you need to perform Gaussian elimination or row operations. Okay, so once you perform Gaussian elimination, you will obtain reduced row echelon form. Okay, once you get the reduced row echelon form, then you can count the number of independent variables, number of dependent variables. Number of dependent variables correspond to the rank of the matrix, and number of independent variables correspond to the nullity of the matrix. Okay. So first you have, well, this is the algorithm. Let me write it as the algorithm. So first you start with the matrix which is of order n cross n. Then you perform row operations. And you obtain reduced row echelon form. Okay, once you obtain reduced row echelon form, you count the number of independent variables. All right, and you also count the number of dependent variables. Dependent variables. Number of independent variables correspond to the nullity, and number of dependent variables correspond to the rank of the matrix. All right, so this is the process. This is the algorithm. These are the steps that you need to take while solving such kind of questions. All right, so let's do this example. So let's do this example. Okay, so what are the row operations that we are going to perform on this matrix?
R2 becomes R2 minus 4R1 and R3 becomes R3 minus 2R1.
Correct. So first row operation that you apply is R2 minus 4R1 and R3 minus 2R1. All right. It is 1, 2, 3, 0, minus 3, 6 minus 12 minus 6. And once you subtract twice of R1 from R3, you are left with 0 row. Correct? So now we are left with 1 0 row, and there are 2 non-zero rows at the moment. Now but it is not in the reduced row echelon form. So we will keep on applying the row operations until we obtain the reduced row echelon form. All right. Now let's perform the reduce row, the row operations. What can I do?
R2 by R minus 3.
R2 by minus 3. Correct. So if I do that, I will get 1, 2, and the last row remains 0, 0 because I will change that. First and the last row remain same. So I will get this matrix. Now I have one entry at the pivot entry. The first entry of each row is now 1. So that condition is satisfied. All the zero rows are at the bottom. That condition is also satisfied. Now what is remaining is to make rows make 0 in the column where the pivot occurs. Okay. So now let's do that. So for that, what operation should be applied? R1 minus 2R2. Correct? So we will get 1, 0, 3, 0, 1, 2, 0, 0, 0. Okay. Now my question to you is this a reduced row echelon form?
Yeah, it is.
Correct.
Yes.
It is a row reduced echelon form, reduced row echelon form. Now what are the, how many independent variables are there?
1.
Correct. How do you count
One
them?
one independent and
Yes.
Uh,
And how many
two
dependent?
dependent.
the 3 will also get, the 3 will not be the same, right?
Yeah, that
It
is
will be
minus
minus 1.
Yeah. Sorry, my bad. Thanks for noticing that. So it will be 3 minus 4, so it will be minus 1. Correct. Yeah. So there are two dependent variables and one independent variable. Right. So what would be the nullity? So nullity
Nullity is 1 and rank is 2.
nullity is 1 and
Ask one more thing. In
yeah, please.
RREF, usually we say ki, there should be 0 above and below 1. Then
Correct.
here it is minus 1 in the third column. Then
Yeah.
the 2 has to be 0 now. Then
No. Only the pivot. So pivot, what is a pivot element? Pivot element is the first entry of the non-zero row. That should be 1. And the column in which the pivot element appears, that column has all the other entries to be 0. So there are only two pivots element. This is the first pivot element, this is the second pivot. Only in these two columns, okay, the first column and the second column, all the other entries, then pivot element should be 0. Okay.
okay, got it, sir. Thank you.
Yeah, but in the third column there is no pivot. Is there any pivot element in third column? No. So
No.
we cannot do anything. So it can be remain as it is. Okay. So now what can anyone tell me what is the nullity? What is the null space of this matrix? How do we calculate null space of this matrix? So for null space,
X minus Z equal to 0 and
correct. X minus Z, X minus
Z equal to
X minus Z is equal to 0. Correct.
Y
So
plus 2Z equal to 0.
X minus Z equal to 0 and Y plus 2Z equal to 0. Now these two equations will give us the nullity. So nullity, this will give us X equal to Z and this will give us Y equal to minus 2Z. So as you can also see, while solving for null space, you can notice that X is written in terms of Z, Y is also written in terms of Z. So in this way, we call that X and Y both are dependent on Z, and Z is the only independent variable. Okay. In case if you are wondering how to find out the independent and dependent variable. And what will be the null space? What is that subspace? Null space of A.
It will be a span of
X, Y, Z. Sorry. So what is X? X is my Z. Y is my 2Z. And Z is Z. And Z is varying in R. Right? So this is my null space. And if I ask you what is my null space, basis of my null space, okay, that is the second question. So what would be my null basis of my null space?
1
You
minus
can
2.
take- Sorry.
We can put Z is equal to 1 and get 1 minus 2, 1.
Correct. So my basis for null space. Yeah. Let me shift everything a little bit up. No. So basis for null space would be uh, one minus two, one. All right. So yeah. Okay.
So, sir, can we find the null space from the reduced echelon form?
Null space from the
Reduced echelon form.
reduced echelon form. Yes, you can do that.
Okay, thank you, sir.
Yeah, but we reduce to row reduced echelon form because it is much simpler while in calculation to deal with this. Okay.
Okay, sir.
Yeah. Now let's do question number 3. Question number 3 says rank of a matrix A equal to what? So it is a theoretical question. So you need to answer me what are the correct options. I will give you some time to think about it. So rank of a matrix A is equal to the row rank of the matrix, column rank of the matrix, nullity of the matrix, number of
Option
dependent
number
variables.
1, 2, and 4 are correct.
1, 2,
1,
and
2, and
4.
4.
Correct. So as we have seen in earlier example that number of dependent variables is equal to rank. Row rank and column rank both are same and they are equal to the rank of the matrix that we already know. So this 1, 2, and 4 are correct. Now rank and nullity of a linear system of equation. Okay. So you have given a system of linear equations. How do you find out the rank and nullity of this system of linear equation? So in particular, first you need to construct the coefficient matrix. Okay. So what would be the coefficient matrix of this system of equations?
3, 2, 1 will be the first row, and
All right.
0, 2.
Two?
Sorry, 0, 1,
0,
1,
1.
1, 1. Yeah.
Right. So it is a 3 cross 2 matrix. Is it correct?
2 cross
Is
2
this
cross 3 matrix.
right? It is a 2 cross 3 matrix. Right. So this is correct. Right. Now let's now let's find out the null space of this matrix. Okay. So what should I need to perform row operations to get the RREF form. So I can first interchange R1 and R2, right? So that I get 1, 0, 1, 3, 2, 1 below. And now let's subtract R2 by thrice of R1. What will I get? 1, 0, 1, 0, 2, and then minus 2. Correct? And what should I do now?
2 by 2. 3 by 2.
Right. So it is. Okay. Now what is the nullity?
Nullity is
1.
1.
All right. Now, what is the null space?
We can write first x plus z is equal
Minus z plus z.
So for null space, x1 plus x3 is equal to 0, and x2 plus x2 minus x3 is also equal to 0. All right. From this, we know that x1, x2 both are dependent on x3, and if I try to express that, it will be minus x3, comma
x3.
x3, comma x3. X3 varying in R. So which one is correct?
first
Which option is correct?
First one.
Correct. First is correct. All right, good. And what is the nullity? Because nullity is the dimension of the null
One.
space or number of dependent variables. How many number of dependent variables are there? There is only one. Sorry, number of independent variables.
1.
Sorry,
Dependent are 2.
correct. So the rank is 2 and nullity is 1. All right. Okay. So I think it is clear now. Okay. Now let's discuss a linear map. What is a linear map? So a map from two vector spaces V to W is said to be a linear map, said to be linear if it satisfies these two conditions, which are called the linearity conditions. So first condition is that T of V plus W is equal to T of V plus T of W. The second condition for all, or better, let me take V1, V2, V1, V2, for all V1, V2 in V. The second condition says that it is compatible with the scalar multiplication, which means you can take C out, where C is any real number and V is a vector in vector space V. So any map satisfying these two conditions is called a linear map. Okay. All right. So some of the properties of linear map that you can directly use to check that whether it is a linear map or not. First property is that if it is a linear map, it will map 0 of vector space, which is the additive identity of vector space V, to 0, which is going to be the additive identity of vector space W. All right. Another thing that you can check, which is an equivalent condition. So the second condition that I'm writing is equivalent is V plus AW, V plus CW is equal to TV plus CTW. So this is an equivalent condition if it holds for any C in R and VW in B. All right. So now let's see some examples. So this is the first example. It is clearly a linear map, so there is no doubt about it. You can think of this map as the rotation of your R2 plane by 90 degrees. Okay, so it is a linear map. All right. Another non-example would be Tx equal to xy. Why can anyone tell me why it is not a linear map? So let's check.
T of Cx comma Cy will be C square xy, but C times T of xy is Cxy.
Right. Correct. So what he is saying is that if it is suppose it is a linear map, then it should satisfy this condition, that while multiplying a scalar to the vector, the C must come out. All right. But let's see what is happening. So if I multiply C to this, so it is Cx comma Cy. Okay. And if you apply T over it, so we will get C square xy. But on the right hand side, you will get C times xy. Clearly, C times xy is not equal to C square of xy unless C is equal to 1. So you can take any other C which is not equal to 1. So then it wouldn't be satisfied. So this is not true for
So why C
T.
square?
What is T of Cx comma Cy?
Like if you take common, then C will take common.
No. You apply this map. Now this is the definition of the function. Both coordinates are getting multiplied under this function. So
I think on the
no,
right hand side it should be C square, right? Rather than the left hand side.
No. This is correct. So I am assuming this. Assuming that it is a linear map, so it should satisfy this second property, and then I'm giving a contradiction. It does not satisfy the linearity property. So thus, T is not a linear map. All right. you can check the first property also, that it does not satisfy the first property. You take two vectors here, x1, x2, y1, y2, and then you add them up. Okay, you will find out that it does not satisfy the property. The right hand side won't be equal to the left hand side. All right. So what is injectivity? Can anyone recall what is injectivity and what is surjectivity?
For injectivity, if f of x1 is equal to f of x2, then x1 should only be equal to x2. That is the case.
All right. What about the subjectivity?
Where we can say like range is equal to the codomain. Like all for
Correct.
all possible value, we have some inverse possible in the domain.
Yeah, inverse does not make sense because for inverse to exist, it needs to be a bijection. But
Okay,
yeah,
so
I
we can
understand.
call pre-image, right?
Yeah, pre-image is a better one.
Yeah.
So injectivity and surjectivity, I take the definition directly as it is from the set theory. But yeah, so injective. So T for injectivity, T of V, if it is 0, if and only if V is 0. Okay, this is what the injectivity definition is equivalent to in the case of. So let me write it better. So a linear map from V to W is injective if and only if, or it is equivalent to say that T of V is 0 if and only if T of V is 0. Okay. So this is one statement, and injectivity is equivalent to this statement. Okay. Now surjectivity. So one of the things that he mentioned, that surjectivity, the range of T. Now what is the range? Range is set of all vectors W in W says that W is equal to okay, this is not the right word. So range of V is TV. Okay, where V varies in vector space V. Okay, so this will be an image, this will be a vector in W. So it is a subspace of W. All right. So if range of T is equal to W itself, okay, then T is called a surjection. All right. Now let me define what is called the kernel of T. So kernel of T is set of all vectors V in W such that TV is equal to 0. All right. So it is in some sense the null space of T. Okay. Kernel is also equivalent to the null space of. So yeah. So clearly it is a subspace. Now can anyone guess? It is a subspace of which vector? Is it a subspace of domain or is it a subspace of codomain?
Domain.
Correct.
Domain.
It is a subspace of V. All right. So yeah, and from this definition itself, from this equivalent condition, from this condition, we know that T is injective. T is an injective map if and only if kernel of T is a zero subset. Kernel of T is zero. Yeah, it is generated by zero vector. That is the right way to write. Okay, so does everyone understand?
Like if nullity is 0, then the linear mapping will be injective.
Yes. Yes. Correct. Good. All right. So let's box out these statements. So these are all facts. This is the definition, and this is also.
Sir, one small clarification.
Right. Yeah. Go ahead.
The last statement that you have written, T is an injective map. If the kernel of T is 0,
right,
that means that none of the vector in the domain.
Right. Other than 0.
When you mean other than 0, is it the 0 vector like 0, 0, 0 of
Yeah,
that
yeah.
domain?
That vector. Right. So when I write 0v, so what happens is vector space V may not always be Rn or Rk. It can be like, let's say, some polynomial space. That is also a vector space. It could be a vector matrix. Okay. Matrix space, matrix 2 cross 2 matrix is also forms a vector space. So in that case, so each vector space has a additive identity, okay, which we denote by 0v. But in practicality, we write it like this. This is the shorthand. This is the notation for that. If you are working with vector space which is Rn or R2, R3, then it will be 0, 0, 0, 0, 0. Okay. Or if you are working with, let's say, matrix which is 2 cross 2 matrix, then it would be 0, 0, 0, 0. Basically, 0 matrix of order 2.
Okay.
Yeah.
So
that's why I'm writing. This is a general notation. I mean, that's why I'm using this.
Okay. So if we take a system of linear equation like Ax is equal to B,
right,
there is no x vector which is other than 0, 0, 0.
Correct.
Okay, thank you.
Right. Okay. I hope
Sir.
this makes sense. Yeah, please.
I didn't understand how we are seeing surjective.
So surjective is same as your range. You understand the range, right? What is the range?
Yes, sir.
So if the range is clearly a subset of W. That is also clear to you. Yeah, you will get this PDF. I upload it on the live sessions notes. So range is a subset of W. All right. So you understand this point. Range is a subset of W. This is clear to you, right?
Yes, sir.
Okay. So now, because it is a subset, this range is a subset of W. It can be any type of subset. So if it is equal to W itself, okay, because W is a subset of itself, you agree to this fact, right? So what may happen? W range can be equal to W. If that is the case, then
so if our domain covers all the possible things present,
all the
in
possible
range,
points in W, right?
Okay.
Then it is a surjective. Okay. Okay, good. Now let's do this question to make you more comfortable with the above statements. So this is question number 3, I guess. Okay, let's stop following the code. Let's say this is 5. Okay, so let's do question number 5, which says that T is a linear transformation from R3 to R2, and T is defined to be x, y, z is equal to x plus y and y plus z. Okay, now which of the following are true or false? Okay, so let's see. So is 0, 0, 0 maps to 0?
Yes, sir.
So first one,
Okay.
third one,
second one.
Is second also true? Let's see. T1 to 3 is 3 plus 5. No, second is also true. What about third one?
It is also true.
Third is also true. Correct. Fourth one?
It is false.
Fourth one is not true because what is 1, 1, 1? because T111 is equal to 2,
2, 2.
comma 2. So this is false. Now, is it an injective map?
No.
No, sir.
No, sir.
Okay. Can you give an example?
T of
Transformation of
Space
1 minus 1 1.
1 minus 1 1. Correct. So if you take, so clearly this is a non-zero element. Okay, this is not equal to 0 0 0. And if you apply T over 8, you will get 0 comma 0. So by this 1 minus 1 1 should be in the kernel of T. All right. So this clearly implies that kernel of T is not equal to the kernel of T is not equal to only the 0 element. Okay, only the 0 0 0 element. Okay, because it has non-trivial element also. So this is also
So
false.
how did you check like 1 minus 1 1? You can check any vector, na?
Yeah, you can check any vector. If you can find out a quick example, that is a good for you. But you can check for any.
But how to find?
Yeah, you just apply it to the equation, right? So just equate it to 0. So this should be 0, right? X plus y plus z has to be 0.
Okay.
So let's solve this. So it is now it is a linear system equation. Correct? There are two variables, two coordinates. So it becomes a linear system
Yes,
equation of order what?
Now
Now
here
you can solve. Yeah.
from here
Now
we
if you-
can take values. X is equal to 1
Correct.
and y is equal to
Correct.
minus 1 and z is
Right.
equal to 1.
You can do more with this. You can find out the null space of this system of equation. Okay, and you can find out the kernel of T. Okay, so let's do that. So let's find out the kernel of T as a subspace. What exactly is the kernel of T? So for that, T x y z is should be equal to 0 0. That's the first step. Now what is x plus y plus z? It is x plus y plus z, which is equal to 0 0. This corresponds to system of linear equation, which is this homogeneous system of linear equation, which is this. Now from this it is direct. You don't need to. You can do the RREF form, or you can directly. So what is the corresponding matrix to this? The corresponding matrix is 1 1
0
0 0 1. Okay. Now it is not in RREF. You can quickly apply one operation and make it RREF. So just subtract R1 minus R2. So we will get 0 0. Sorry, 0 minus 1 0 1 1. All right. Now you can see what is the solution.
Won't
Sorry?
we separate the coefficient matrix and the constant one? Like by the line that we draw in a Gaussian elimination.
No, I think here there are 3 variables involved. That's why you see 3 columns.
No, the okay, nothing. Sorry.
Okay. Okay. I hope your answer you got answer. Okay. So now we got this RREF form. Now let's solve this RREF form. So you can clearly see that y is equal to minus z and y is equal on n and x is equal to z. Okay. So this is your solution to the null space calculations. So the kernel of T would be just z minus z and z. Z is in R. So
1 minus 1 1.
correct. That would be your basis, and generated by that would be your whole space kernel. All right, good. So it is clearly not an injective map because the kernel is not equal to the 0 subset. Okay, 0 subset. Okay, now let's do this question.
Sir,
Yeah.
so kernel is basically how we were calculating a null space.
Yeah.
And I
So
didn't
I will
understand
talk
this
about.
part.
So I will. So yeah, I'm going to discuss how to associate a matrix to a linear transformation. Now, once you can associate a matrix to the linear transformation, the kernel of the linear transformation will be equal to the null space of that matrix. Okay. So I'm going to do that.
Yes.
So
Yes,
what I'm saying is that given a linear transformation, let's say T V W, you can associate a matrix to it. Okay, suppose this is n dimension, this is n dimension. You can associate a matrix which is m cross n. Okay, and the kernel of T would become the null space of this A. In particular, they would be equal, and image of T or range of T would become the range of yeah, range of T you don't need to calculate. You can directly calculate from this. But kernel of T would become the null space of A. Okay, so that we are going to see.
yes, sir.
Before doing that, let's. Are there any other questions?
So for checking whether a given linear transformation is injective, you want us to check whether the zero vector is just the zero, or if there is anything more than that. If it is, then the kernel is more than one.
Yes,
So in that way, we can prove that it is
it
not
is not one.
injective or it is
Correct.
injective. What should be
Correct.
the approach for surjective?
For surjective, you need to find out an element in W which cannot be written in terms of the image of any vector in V. Uh, yeah, in this case, it is not surject. It is surjective. But let's say, okay,
An
I
example would
don't.
be equals.
Yeah, I will try to give an example if I find one.
Okay, no problems. We can continue the flow in case if we have time. We can.
Yeah. Let me give a quick example. Let me form an example and then. So map. So let's see. Let's take this map from R2 to R3. Okay. So think of this xy equal to x plus no, x plus y plus y minus 2x, or y minus 2x and 3. Okay. So 0. All right. Let's take 0. So okay, so now you can check that this is a linear map. All right. So T is linear, but not surjective. Okay. And how to see that? Because can you guess any element in R3 which cannot be written as image of this T?
Yeah.
Element in R3 where z not equal to 0.
Yeah.
Yeah, correct. So you can see that the third column is 0. So
Zero.
you try to make an element. You try to find out and write an element which is in third quadrant is not equal to 0. So anything would work, right?
So
Suppose if there is x in the third column. Now can you find out an element which is not in the image of R2?
So again, you want us to equate this to 0, 0, 0, is it? X plus y is equal to 0, y minus 2, x is equal to 0, and x is equal to 0.
No. If you do that, then you will get the null space.
Yeah, okay. Yeah, then I'm going towards checking whether the function is, transformation is injective or not. Yeah, how do I check that? Looking at the transformation x plus y, y minus 2x and
So
x, it
can I
doesn't
write this
include
form linear transformation in matrix form and then check
Yeah, you can do that.
like
So
1
if it
1
is
0 1 sorry minus 2 1 0 and 1 0 0,
right.
and then check we can check na if nullity is 0 then injective, otherwise surjective.
nullity is 0, then injective. Otherwise, no, it doesn't work. It is not either. Nullity is a proper injectivity is a property of the domain. Surjectivity, well, basically, it's both of them are property of the linear transformation, but it is not like that. If it is, so
So we
so
can
there
take,
is,
for example, 2, 1, 0.
yeah. Sorry.
Like in R3, we can consider 2, 1, 0.
Right.
And when we try to do that, like we'll be getting some absurd results.
Correct. So you can, so what you can do, you can take some value right here. So let's say 1. So the one that is suggested 1, 2. So let's take 1, 1, 0. Okay. Let's try to see whether this is in the image of T or not. Okay. So what will it say? It has to be equal to this. So x is equal to 0, and x plus y should be equal to 1, which would imply that y has to be 1. Okay. So this is in the image. Bad example. Let's take it to be 2. Okay. Keep it to be seen, and then 2. So this would imply that x plus y has to be 1, which implies that y has to be 1. But because of the second coordinate, y minus 2x, it will give me 1 minus 0, which is 1, which is not equal to 2. Okay. So so this 1, 2, 0 is not in R3. Okay. Yeah. So it is not going to be surjective. But you can notice. So there is another method, because this is like a guess.
Correct.
You are guessing, right? The correct way should be to find out the matrix, coefficient matrix, find out the rank or nullity, because these are odd dimension. So their dimension by rank nullity theorem, their rank plus nullity will be equal to 2 only. Okay. So what is a rank? Rank is the dimension of the range. All right. Rank of the matrix is dimension of the range. So, and that is going to be the subspace of R3. So unless the dimension of the subspace, dimension of the range is equal to 3, unless that happens, it cannot be surjective. All right. So rank cannot be 3 in this case, because it has to be always smaller than 2. Okay. So what I'm saying is that rank of T will always be bounded below by 2, because of the domain. Dimension of the domain is 2. And for surjectivity, the rank of T should be equal to the dimension of the W, which is the codomain. And in our case, dimension of W is 3. So rank cannot be 3. So it always be non-surjective.
Okay.
Or
So
we
makes
can
sense?
say, like we are trying to map something with lesser cardinality,
Lesser dimension.
yeah, to greater. So
To
it
the-
cannot be.
Yeah. So there will be extra vector which will always make a problem. But yeah, theoretically, this is what is happening. So you can always, the rank, how to find out rank. And then once you know the rank, you can compare it with the dimension. So that's how you make a guess whether it is going to be surjective or not. So without working out exact example, and once you know that it is not going to be the case, you can either write this argument or you can give a counter example like this.
So few statements just to confirm my understanding. In this transformation, we are going from R2 to R3. Does that mean
Right.
that any transformation from R2 to R3 is always not going to be surjective?
Correct. And the reason is this. This is the reason.
Okay. In other words, let's say if it is going from R3 to R2, then
Then
there
it
is a
could be.
likelihood it could be surjective,
Right.
and it is
Correct.
must be surjective, right?
Correct.
Okay. And any transformation, if we get in an exam, then we can take this approach that we form the matrix and find the rank.
Right.
If the rank is not the full rank, or rather, if we
Right.
find the rank,
Not
if the rank is not matching to the dimension of the codomain,
correct.
then it is safe to say that it is not a surjective.
Right.
Okay.
Yeah, this is a correct argument.
Okay. Thank you.
Yeah.
This is very helpful. Thank you.
All right.
So
Alright.
one query.
Okay.
So like if we have any matrix of m by n, then, and if you have a full rank, then it is injective. But what is the property for surjective?
If you have a matrix of order n cross n, right,
Yes.
and it
Yes.
is injective.
Like if we have full rank, like
Huh.
nullity is 0, then it is injective.
Right.
What is the property for
But
surjectivity?
yeah, so whenever you say surjectivity or injectivity, there has to be some associated linear transformation. Okay.
Okay.
So you need to so whenever you have a matrix, the corresponding linear transformation is always ax equal to the transformation is defined by tx equal to ax. All right. So whenever you have matrix, your linear transformation is defined by ax. All right. So in this case, the surjectivity, because it is full rank, so surjectivity will be a surjective matrix. So when you say your matrix is n cross n, what does this mean? That your T is defined from Rn to Rn. All right. And you are
Yes.
saying because it is full rank, so what is the
So, but
rank
m
of
by
the,
n, na, so m by n, then it should be t from Rm to Rn. Na?
okay, it is m by n. Okay. So it is from Rn to Rn, correct? So now if it is full rank, so what is the rank? What the maximum rank would be n,
N.
right?
Yes.
And if m is larger than n, then it could never be surjective. Okay.
Yes.
Otherwise, if m is equal to n and rank of t is equal to n, then it is surjective. All right.
Okay.
And yeah, these are the, and if m is smaller than n and it is full rank, and rank is equal to m, let's say, then it could also be surjective. In this case, not possible. All right.
Okay, sir.
All right. So now let's see how to associate a matrix to a given linear transformation. So for that, you need to have a ordered basis. Okay, Anukriti, you have a question?
Sir, so if m is equal to n, is it safe to say that it is always surjective, given it will injective, like when m is equal
Yeah,
to
whenever
n?
it is injective, it will be surjective
Okay.
because of rank nullity theorem.
Okay, sir.
Yeah. All right. So linear transformation with respect to a basis. So suppose you have a linear transformation T from V to W, and let's say beta denote the basis V1 up to Vn of basis for V, and gamma is the basis for W. Then how do you express associate a matrix to this? So the associated matrix is defined by expressing each of image of each of basis of the domain in terms of the basis of gamma. So let me write it like this. Sorry, so let's take it to be m. It is m dimensional, it is n dimensional. All right. So the columns will be this. Okay.
Sir, could you
It's
repeat
okay
the last part? I was able to follow up till the beta and gamma are the basis vectors for this vector
Right.
space V and W.
Right.
And
Now each of TVI will lie inside W. Correct. So you can express each of TVI in terms of the basis gamma, which is the basis of W. Right. And that expression I'm calling it to be this way. I'm denoting it to be this.
So when we are actually computing for in any given transformation,
Okay.
what
Yeah.
we should do is
Yeah.
take the value of beta and put it in the transformation, and we get an output. And that output we have to express it as a
In
linear
terms of
combination of the bases given in gamma.
correct. And the coefficients that you will get in terms of gammas, that will be these are the coefficient matrices.
Columns.
Yeah, the columns will be the coefficients in terms of the each image of the basis vector in terms of the basis of W.
Will you be able to solve one problem, sir?
Yeah, I will. Let's
Okay.
see. I have. Yeah.
Thank you.
Okay, so let's say in this question itself, we have given. I hope everyone can see this question, right? Let me enlarge a bit. Okay, so we have given this question. So from R2 to R2, and we have given the basis as well. The basis is the standard basis. All right. So now let's express. Yeah, it is the other way around. It is already expressed with respect to this in terms of that. So now what is the following appropriate definition of T? Okay, so let's do that. So you have already given matrix associated to the linear transformation. You need to figure out what linear transformation is this. So whenever you have a matrix, you define the linear transformation by Tx equal to Ax. Okay, now what would it be? Repeat 2, 3, 1, 4 x y. It will give you 2x plus 3y, comma x plus 4y. Okay, so what is the correct answer?
Fourth one.
Correct. Now let's do the other way around. Let's take this linear transformation. Okay. So what is the linear transformation? Txy equal to 2x y plus 3x minus 4y. All right. So this is a linear transformation defined from R2 to R2. Suppose domain. So this R2, the domain R2 has basis beta given by 1, 0, 0, 1. And the codomain has basis given by 1, 0, and let's say 1, 1. Okay, I've changed the basis. I'm not taking the standard one for the codomain. All right, now we need to express T with respect to these bases. Okay, so let's go by definition. So codomain, call them to be V1, V2. So now, and this is my W1, W2. Now express your WV1 in terms of W2, W1. W2, W1. Okay, so first let us see what is VT, VW. TV1. What is TV1? It is 2,
3.
2, 2, 3. Yeah, 2, 2, 3. Right. And if you try to express it in terms of W1, W2, so let's say this is A times W1 and B times W2. So what will you get? You will get 2, 3 equal to A times 1, 0, B times 1, 1. And it will give you some system of linear equation. You can either solve that or you can directly write down the value of AB. So it is up to you. Can anyone tell me what will be AB?
A is minus
minus 1, 3.
B is 3.
All right, correct. So it is minus 1 and 3. Okay, now what about TB2? TB2 is
1
TB2
minus
is
4. 1 minus 4.
1 minus 4. Correct. And now express it in terms of 1, 0 and 1, 1. Okay, so let's solve it by using system of linear equation. So what would it be? It will be system of
5
equation will give
minus
us
4. C is 5, D is
okay.
minus 4.
Okay. So C plus D is equal to 1. Second equation is D is equal to minus 4. Right. So using this, you will get C is equal to 5 and D equal to minus 4. Correct? So what will be your corresponding matrix A? Corresponding matrix A will be the coefficient. So first I need to write coefficient matrix for T1, sorry, TB1 and then TB2. So what is TB1? Coefficient matrix of TB1, it is, can anyone tell you what is the matrix?
First column is -1, 3.
Okay,
Second column is 5 minus 4.
correct. Does everyone agree with this?
Yes.
Okay, I hope it is clear to every one of you. Okay, all right, good. So I have already discussed images and kernel. So let's do this example. Okay, so I have already discussed what is an image and a kernel. Now let's come back to the fact that, yeah. So after associating matrix to the, so what we have done, we have associated, given a linear transformation V to W, we have associated a matrix to it, which is of dimension m cross n, of order m cross n. Now we have defined what is a kernel of T to be the set of all x in V such that Tx equal to 0. So this is equivalent to the null space of A. All right. Similarly, yeah. So I can define rank of a transformation as the rank of a matrix A, and I can define nullity of T as the nullity of the associated matrix A. Now this associated matrix is important to notice that it is dependent on the basis. So what basis we have used is gamma beta. Okay. So it is dependent on gamma beta. If you change the basis, the associated matrix will change, but the rank and nullity are invariant under those changes. So it doesn't matter. Okay, whatever basis you choose. All right. And similarly, there is another theorem. There is a theorem called rank nullity theorem, which says that rank of T plus nullity of T is equal to dimension
N.
of V.
Dimension of n.
What is it?
N is range, like V.
Yeah, dimension of V, right? In terms of matrix, it is rank of A plus nullity of A equal to the number of columns in A. Now, what is the number of columns in A? It is n in our case. So let us write number of columns of A. All right. Okay. So now let's move on to this question. So in this question, consider the linear transformation T from R3 to R3. T is given to be, let me enlarge this question. Okay, is it visible to everyone now? Okay, so let me know what is the correct answer. Okay, how do we solve this problem? Can anyone tell me?
Should we consider starting like constructing the matrix for this?
Correct. So as you can see, I have written it down as system of linear equation. All right, x plus y plus z is equal to a. Okay, basically I'm writing the image as ABC, and I'm comparing the I'm comparing the coordinates. While you do so, you will get this system of linear equation, which consists of three equations, linear equations. All right, now you can write down the augmented matrix of this, which I have done, and then you can try solving this system of equation until you obtain something which is familiar to you. Now you can see that it is coming out to be 0 because it has nullity. This is nothing but the RREF form of the corresponding matrix A. Okay, this is my coefficient matrix A, and this is the RREF of A. You can see that the nullity is it has nullity. Nullity is non-trivial. So whenever nullity is non-trivial, you know it is not injective map. So the range could not be the whole space of R3. So this is clear to you. All right. So now you can just use this last equation that you are getting A plus B, C plus B minus A is equal to 0. Use this. So it should be equal to 0 if you compare, right? The coordinates. It should be equal to 0. And if you see, then this is what you get as a relation. Okay. So this is the relation that you get after comparing, and thus the image is set of all points x, y, z in R3 such that x is equal to y plus. Okay. So what would be the correct answer? First one. Now, what is the rank of this matrix? Just calculate the number of. What is the nullity? Once you know the nullity,
Rank is 2.
rank is 2. Right. So option 1 and 3 are correct. Is this fine with everyone?
So third line in third row, it can't be possible, right? It can't be possible, right? Because it's a
It
zero
can be
row.
possible unless it is equal to 0, right? It is possible unless this is equal to 0.
But
That
it's
is what
a
I'm doing.
zero row.
Yeah. So the third row makes sense if C plus B, B plus C minus A is equal to 0. All right.
Okay.
So that's why I am putting this condition. That's how I am getting this condition. And once you get this condition, you can solve this. Okay.
So this condition we can derive from the first row also. Na x is equal to y plus z.
How?
But in first row we have a also.
Yeah, that's why I'm solving this.
Okay.
You cannot arrive from the first equation. That's why I'm solving this. So this, yeah. Okay.
Sir, I forgot. Can you go up a little bit?
Yeah.
So to determine the range of a given transformation, we have to
Yeah.
express this in the linear equation, convert that into an augmented matrix, then convert that into a reduced row echelon form.
Right.
Whatever that we are getting on the B side of AX is equal to B, that we are equating to find out what is the image. Now in this situation, it is all aligned in a form that C plus B minus A is equal to 0. But in case if it doesn't, how do we approach?
Yeah. So what may happen is this row might not be 0. Okay. And when will that be the case? When nullity is not equal to
0. Sorry.
Nullity
is 0, right? In that case,
nullity is 0. Right. So when nullity is 0, rank will be 3.
Correct.
So the answer to this would be all x, y, z in R3. So you can obtain everything because the rank of the matrix or rank of T is equal to the dimension of the codomain. So then the answer, then you don't need to do all these things. This will only work if there is a nullity.
Okay.
Right. And whenever you have a nullity, then only you can, then you need to determine the exact subspace. Otherwise, you don't need to do.
So in this specific example, should so the underlying truth is that this particular transformation involves only two elements of a dimension, not the third one?
Yeah, because it is a rank 2. That's what
Okay.
rank says.
Okay.
Yeah. All right. So
So
we have
can I
already.
say this transformation is surjective?
This is not surjective. If it was surjective, then the image should be R3. All right, Bhumi, what is your doubt?
So in the second row, you didn't divide it by 3. Can I get the answer why?
No, but you don't need to. So you don't want to solve this. You want to find out condition to make this solution consistent. That's what you want. So to make this system of linear equation consistent, you need to have 0 here. Otherwise, it won't be consistent, right? So that's why I need to focus on this row. Other rows I don't know. Other rows are there to just find out the rank of the matrix or transformation. All right. Now, can anyone tell me what will be the basis of this image? So you can express. There are two. Now x is dependent on two variables, so you can express y is equal to y plus z, y and x, z,
Yeah.
right? And once you do that, now you can express it as further. You can think of this vector as sum of
y
two vectors.
y 0, right?
Sorry. Combination of two vectors y 0 plus z
Right.
0 z.
Right.
All right. And now what you do, you can take y out and you will get one vector, and you can take z out, you will get this vector. Now this is nothing but the spanning set of these two vectors, 1 1 0 and 1 0 1. All right. So what will be the basis? So basis of image of T are 1 1 0 1 0 1. All right. This is how we find out the basis. Earlier, I've already discussed how to find out basis of null space, so I will not going to do that. So this part is done. Done. Okay, now let's see the change of basis matrix. So suppose you have yeah. So for change of matrix, let me first recall.
Sir. So can you scroll a little up, sir? Previous one.
Is this fine?
No, sir. The previous problem that is solved.
You will get notes of this, so you can do it later. Let me, because I have very little time remaining and I need to cover a lot of topics, so let me speed it up a bit. All right. So change of basis or equivalent matrices. So let me first recall the definition of two equivalent matrices. Let A and B are M cross N matrices. A is said to be, matrix A is said to be equivalent to B if there exists an invertible matrix P and Q such that B is equal to Q AP. Okay. Now, what is the order of A? Order of A is N cross N. order of P is n cross n. What would be the order of n cross P?
N
It is
cross
n
n.
cross, and Q order is n cross.
N
All
cross
right.
n.
So, all right. So now let's say you have two linear transformations. Let's say T1 from V to W and T2 from V to W. Okay. Sorry. You have a linear transformation from V to W, and you have two set of bases on V and two set of bases on W. All right. And beta 1, which is, let's say, V1, 1, V1, 2, up to V1n, is one set of bases, and beta 2 is another set of bases, V1, V2, 2, V2n. These are two set of bases on V. Similarly, there are two set of bases on W. All right, W1 up to Wn. All right. Don't think of it as a square or something. This is just a notation. Okay? Don't confuse yourself and yourself. Okay. So there are two set of bases given. Now let's say A is a matrix that is given with respect to beta 1, gamma 1. Okay. So my notation was gamma 1, beta 1. So let's stick to that. And let's say B is a matrix which is given with respect to gamma 2, beta 2. All right. So now these two matrices correspond to the same linear transformation, but they are different but they are expressed different because they are expressed with respect to different matrices. So what I can do, so there exists invertible matrix P and Q. So P matrix, so I need to find out matrix P such that if I multiply with A and matrix Q, so I get matrix B. So matrix B is gamma 2, beta 2. Matrix A is gamma 1, beta 1. Matrix P is, yeah, now I need to figure out what is matrix P. So matrix P, if you look at on the right hand side, on the left hand side, it is beta 2, gamma 2. So the vector that you will apply will be expressed in terms of beta 2. So the same vector will be applied over here. It will be expressed in terms of beta 2. Okay. So yeah. So then I need to apply a matrix which will convert my basis from beta 2 to beta 1. Okay. I will express that in. And now I want the result in terms of gamma 2. So I need to have some machine matrix over here which will convert the result of this matrix, which is going to be in gamma 1 to gamma 2. So this is what Q does. So Q is matrix. It is a machine which takes entries in gamma 1 and it returns you back in gamma 2. Okay. So this is how I denote. So I hope the notations are clear.
So just to
And
confirm, you said the matrix P is formed by taking the basis B2 and converting it into B1.
Right.
And Q is like gamma 1 it takes in and then converts to gamma 2.
Right. Okay. Right. Correct. Exactly. So, and now we already know how does this matrix will look like, because we know the domain and we know the codomain. All right. So we will express beta 2 in terms of beta 1. And in this case, you will express gamma 1 in terms of gamma 2, and the columns will be the coefficients in the under that in those expressions. Okay. So this is how you do it. So I will not go into detail of this, but let me state another fact. So you will get to do problems in the TA sessions as well. So don't worry. I'm here to recall the theoretical part mostly. If time permits, I will discuss an example, but let me cover the theoretical part first. Okay. All right. So yeah. So matrix A is equivalent to matrix B So these are following statements are equivalent. Following statements are same. That's what it means. So A is equivalent to B. It is same as the rank of A is equal to rank of B. Okay. The third statement is A can be transformed to B by finite sequence of row operations. Sequence of row or column operations. All right. So these three statements are same. So either proving that they have the same rank.
Dimensions also same na.
Yeah, that's what I said. Rank is same.
Yes.
Yeah.
So A is equivalent to B when the rank of both the matrices are same.
Are same. Correct.
And it's always, there is no exception to it.
Yeah.
Okay.
You can, so it is enough to prove that they have the same rank.
Okay.
If you
So
want
could
to
you
prove,
scroll above a little bit? So
you will get these notes.
Okay. In exam, if we get any, if there were a transformation given and with 4 set of bases,
Right.
We just
So
need to
first step will be
calculate the P matrix and then Q matrix, where the P matrix is, we will be taking the beta 2 basis, put it in the transformation, whatever the output that we are going to get, that we will be expressing in terms of beta 1. And then that coefficient of that, we will put that as the matrix P.
Yes.
And same procedure for Q. And
Correct.
once we have that, then should we need to do this Q into A into P to derive B? If B been asked, like, what is the equivalent, find the equivalent matrix for A.
In order to find out A and B, you don't need to do, you don't need to find out P and Q. Okay. You can independently find out A and B. All right. Because you know what is T. So you can express T and you can find out those with respect to this.
If the transformation,
if in the question, if it is asked to find out P and Q, then you need to find out P and Q.
Okay. So what you're saying is, if the transformation alone is given with the 4 set of bases pertaining to V and W, then by applying this notation, what you have given, we can directly compute the matrices pertaining to B and A.
Right.
Where we, okay, understood.
Right. You don't need to go into that much detail unless they have asked you to find out P and Q.
And if we do in that approach, and then if we find the matrices of both these are equal, rank of the matrices of these two matrices are equal, then it is equivalence.
Yeah, they are there.
Okay, understood.
Sir, while finding P, like, should we express beta 2 in terms of beta 1 or a transformation of beta 2 in terms of beta 1? We have to apply T, is it?
No. You don't need to apply T.
Okay.
While finding out P, you don't need to apply T. It is just you express your beta 2, each vector beta 2, each basis vector of beta 2 in terms of beta 1s.
Okay. Right.
Sir, could you repeat that?
Yeah. So, look, in this case, you just need to express vectors of beta 2 in terms of vectors of beta 1. You don't need to apply transformation. Transformation is only applied in this case because you are changing the space as well, because gamma 1 is in the W, beta 1 is in B.
Oh, okay. I misunderstood that I should take the beta 2 basis, put it into the transformation.
No.
Okay.
If you put it into the transformation, then it will be element in W. Then beta 1 is no more basis in W. Beta 1 is a basis in V. So you need to, if you apply transformation, you are changing this base vector space.
Okay.
So beta 1 is no more applied over there. So you cannot.
So in that case, it is much more simple, right? So what you're just saying is express the beta 2 in terms of linear combination of beta of 1 basis.
Correct.
So in this way, we are just restricting the basis within the V or the domain,
Right.
whereas for Q it is within the codomain. Okay.
Right. Okay. Then I misunderstood your question as well.
Yeah. Okay. No.
Right. Thanks, Krish, for clarification. Unless
Thank you.
I might have. Yeah. Okay. Thanks. Thank you, guys, for being attentive. All right. So here is an example of this question. You may try it out once I upload these notes.
Sorry to interrupt again. If you can go up.
Yeah.
But for calculating A and B directly from the given transformation, we still have to apply that basis in the transformation on the basis, right?
Yeah, because you are changing the.
Okay, understood.
Yeah.
Noted. Thank you, sir.
Yeah. Okay. So yeah, I'm not solving this question now because I don't have time. I need to finish half of these slides as well. So I'm skipping this question. I have only half an hour remaining. So let's for similarity. Okay. So similarity of a matrix. Two matrices are said to be similar if there exists an invertible matrix P such that beta is equal to P inverse A of AP. Okay, if you can have this relation, where P is an invertible matrix. Okay, so invertibility. So two similar matrix, if A and B are similar matrix, then they satisfy these three conditions. Okay, so their rank is same, their traces will be same, their determinant will be same. If you have asked for that whether two matrices are similar or not, what you can quickly do, you can find out their determinant. If their determinant is same, then they can be similar. Okay, but if their determinant are not same, you can quickly say that they are not similar. Okay, or you can find out any of these three properties.
So is it any or all the three properties should match?
So if they are similar, any of the three properties are satisfied. These three properties are same. But it is not the case, even though if they are same. If all of them are same, but you cannot say that they are similar matrices.
I'm sorry, sir. I kind of lost somewhere here.
Yeah. So what I'm saying is that if you have given two matrices to be similar, then their rank will be same, their traces will be same, and their determinant will be same.
So these three conditions should satisfy.
Yeah, but there can be matrices satisfying these three conditions, but not similar. Okay.
When you mean but not similar, it will not contain the same elements, or?
No, similar means this. This is what the definition is. Similarity. There exists a invertible matrix P such that this happens. All right. So in order to check, so for matrices of 2 cross 2 and 3 cross 2 order, the square matrix of 2 cross 2 and 3 cross 2, to check that two matrix is similar, if and only if the polynomial that you get by solving this determinant are same. Okay, now what is this determinant? Let's see. So this determinant is determinant of A minus lambda I and determinant of B minus lambda. All right. Now what is this? So for example, let's take this example. Okay. So you have A and B matrix given. Now, are they similar? So let's check their determinant. So their determinant. So for A, determinant of A is 6. What's the determinant of this? It is 4. Right? So it is not equal. So they are not similar. Not similar. All right. But whereas in this case, now look at this example. So determinant of A is 4. Determinant of B is also 4. So determinant is matching. What about the rank? Rank also same. It is 2 cross 2 matrix. It is also rank is also 2. Rank is also matching. Rank of A is equal to 2. Rank of B is also equal to 2. Alright, rank is also matching. What about the trace of A? Trace of A is 4. Trace of B is also 4. So trace is also matching. So all these three conditions are matching. So so they are strongly suggest that they are going to be similar matrices, but we cannot confirm yet. So let's find out the polynomial. So how to find out polynomial? A minus I lambda I. Okay. So what is this? So let's find out. So what is A minus lambda I? A minus lambda is 2 minus lambda. 1, 0, 2 minus lambda. Okay, and you calculate the determinant of this. Similarly, what is the determinant of b minus lambda I? It is going to be determinant of 2 minus lambda, 1, 0, 0. So what is it? What will the polynomial? It is 2 minus lambda square. So again, 2 minus lambda square. So their polynomials are same. They are both are same. So they are similar. Okay, so this option is not correct. This one is also not correct. All right.
So can you scroll up for that condition, sir?
So for similarity, if you want to check whether two matrices are similar, you need to calculate these two determinants. So these two determinants will give you polynomials of degree 2 or degree 3, depending on the order of the matrix. If these two polynomials turns out to be same, then they are similar matrices. Otherwise, they are not same. They are not similar matrices.
In this case, it was same, no? But you said it is not similar.
No, but look at the option. Option says they are not similar.
Okay. Okay.
But it turned out to be similar.
Similar. Okay, in that context.
So that's why the statement is false. Okay.
And is this similarity should the dimension need to be same for the two matrix?
Yeah.
Okay.
They has to be of the they are a square matrix of the same order.
So they must be square matrix only, then we can calculate the determinant.
Yeah. A square matrix and of the same order. Then only we can compare.
In other words, any rectangle matrix, can we say that those won't be similar at all in any given condition?
Yeah, by definition they are not.
Okay.
So you cannot define similarity on rectangular matrix.
And this determinant of a minus lambda I is equal to determinant of b minus lambda I. This is applicable for any type of square matrix that has been asked to compare.
No, 2 cross 2 and 3 cross 2. In case of order 2 and 3, okay, this is equivalent. Otherwise, it is.
Oh, this is applicable only for 2 cross 2 or 3 cross 3, not of a higher order matrix.
No.
Okay. And we are hoping that in our exam we won't be asked any higher order matrix.
Yeah, higher order won't be asked. If there is any higher order matrix, you can go and check these three properties.
Okay, understood.
So it might mostly be the case that they are not similar if they have asked higher order. So you might be getting some of the equality not holding these any of the equality, some of the equality. Okay. So then you can figure out where it is similar. So these conditions are useful to find out whether they are not similar. But if you want to check they are similar, you need to check that their polynomials are similar. Okay, yeah.
If a matrix is similar, it can be equivalence.
Yeah.
Okay.
Because their rank will be same. So rank is same means equivalent. Okay. There was one question from someone.
Yeah, sir. Actually, these A and B are not similar. The second one, because for diagonal, for scalars, you have to have the exact same matrix for them to be similar.
Oh, right.
Also, we were never taught about this lambda I thing. This is the first time we have been introduced.
Wait a second. Oh yeah, you can directly use the condition. Right. Okay, sorry. Sorry for the confusion. Okay. Thanks, Rahul, for pointing it out. Yeah. So, okay, sorry, my bad. I completely made a wrong statement. Sorry, guys. So, yeah. So as he pointed out that you can take one out. So because it's a scalar matrix, and if you use the condition of let's say of similarity. So suppose there exists. Suppose there is P. Okay, suppose there is P So P inverse BP, what would be? It would be, so this is nothing but 2i. Okay, it is 2 times I. So it would be P inverse 2IB, sorry, 2IP. So you can take P out, and you can take 2 out, and then it is P inverse IP. Now multiplication with anything with I will give you the P matrix only. So it is P inverse P. And now P inverse P will again be I. So you will get 2i. So matrix B is always equal to matrix B is always similar to itself, which is P. All right, it cannot be similar to anything else. So yeah, so they are not similar. Correct. So this is a correct option. Yeah. So apparently this statement is false, and okay, I was not aware that this is not being taught. So okay, so let's erase this thing and this thing that I have not taught you. This thing. Okay, sorry for this mistake.
No problem, sir. So in that case, our final takeaway is that if a matrix, if to prove whether two given matrices are similar, we must check the rank, trace, the determinant. If these three are same, then it's a likelihood that it can be a similar matrix. Is there
but
any
that is
other...
not the case.
Okay.
That is not the case because this is the counter example.
So for this counter example, it is to play around with the identity matrix, right? So
yeah, you need to use the definition. So you got this definition, you need to use this definition cleverly in order to. In this case, it is simple because B matrix is a scalar matrix. You can take 2 out, and then what it remains is identity. You can multiply identity, and you will get identity back because P is invertible matrix, so you can play with it. But yeah, in this case, it turns out to be simple.
Okay.
But yeah, usually you will get simpler cases which can be dealt easily. Yeah. So forget that complicated definition that I just gave.
For the matrix, you helped us with one method of like how to compute the P matrix and Q matrix for the to check whether given two matrices are equivalent or not.
Sir.
In this case, how do we verify? How do we compute the P and P inverse?
Oh, that is very hard part. That is not very easy.
Okay.
So let's not go into that.
Will that be asked in the exam or?
I don't think so.
Okay.
No, unless it is very simple.
Okay.
Otherwise, it won't be. Yeah, Rama Ramesh.
Sir, what you told now is the polynomial test. The polynomial test for A and B, both are the same. For A and B is the same, which means that they are similar. But now we are not doing the polynomial test using test. It says it is not similar.
Sorry?
A and B is not similar using identity, but using polynomial, A and B.
No, polynomial test was wrong. Okay, maybe I have not written it correctly. It was wrong, so forget about that.
Okay.
Yeah. So whatever I have written down, that is only the correct thing.
Okay.
That was incorrect.
We need not remember that polynomial test. Sir.
Yeah, forget about it. Okay. Sorry for that. Sorry for the trouble.
So, but in second example, as we see, all the conditions are satisfied, but still it is not similar.
Yeah.
How can I see like this kind of example?
Yeah, because it does not satisfy we go by a definition. Okay, so this is the definition. And
B is equal to P inverse A times P.
Yeah. So if it is similar, then it has any matrix. So for similar matrix, it would be of this form, P inverse BP. And now B is equal to 2i. So if you plug in B is equal to 2i, you will get B back. Okay, you cannot get A back. So B is only similar to B.
We should see for some scalar multiplication also, like here.
In this case, this is very specific case. So you need to go case by case. So yeah, for this example, for a scalar matrix are similar to scalar matrices, to the same. They're similar to themselves.
We can move on, sir. Thank you.
Yeah. Thanks. Okay, sorry for that mistake. Okay, now let's talk about the affine subspaces. Right. So let me recall the definition. Any subset of a vector space V that can be written as U plus W. Okay, where U is a vector, in V, and W is a subspace of V, is called an affine subspace. Okay, so here is how we denote this this addition. All right. Okay, this is what the affine subspace is. So here is an example of the affine subspace. So for example, this set of, so clearly this is a subset of R3. All right. Now claim is that it is a affine subspace. How to see that? So in order to say that it is an affine subspace, I need to find out a vector space W of R3 and a vector U in R3. Okay, so one of the thing in affine subspaces, they don't contain the zero element. As you can clearly see that 0, 0, 0 is not in S. All right. So 0, 0, 0 is not in S. So what? So if you plug in that 0, 0, 0, you must get 0 back. All right. So that would be your vector space W X, Y, Z in R3, which satisfies this equation. Okay, so this is a subspace clearly because it contains 0 as well. But if you want to write it down, it has. So now you need to find out a vector U. So what could your U be? If you take X, Y to be 0, your Z will be 2. So that would be your vector. So 0, 0, 2. Now clearly, if you see that, if you write down the addition of U and W, what will you get? This would be equal to S. All right. So S is an affine subspace. So one of the example of this is the writing down the set of all solution of a linear system of equation. Once you get one solution, you can use that solution and add it to the null space, and you will get the affine subspace. So that is one of the example. All right. So this is another example. For example, this also y is equal to x plus 2z, x plus z. So clearly you can see that it contains, yeah. So it contains 0, 0, 0 in it. So let's say this is again s. So 0, 0 is contained in this, and this is so this is nothing but it is a vector subspace. You can check that S is a vector subspace. It is vector subspace of P, and for this you can take your vector 0 to be vector U to be 0, and vector and the subspace W to be the S itself. So 0 plus S will be equal to S. 0 vector plus S will be equal to S. So S is also an affine subspace. So in particular, any vector subspace is also a affine subspace of V. All right. Now let's recall what is an affine transformation before going into this affine. Before going to the length. Yeah.
You said any vector space is a affine subspace because it inherently contains the 0 vector in it.
Yeah. 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 So you can take your U to be 0, and your W will be that subspace that we are looking at. It will satisfy this condition. All right. Okay, so now what is a linear transformation, affine transformation? So let me recall the definition. Suppose L and L prime are two affine subspaces. Affine subspaces of V, a map F from L to L prime is said to be a map F to L prime with where L is given by U plus U. So U is my U plus W. U is the vector and W is the subspace. And L prime is given by Fu plus W prime. All right. Okay. The map is said to be an affine map if there exists a map G, a linear map G, from W to W prime such that G of U is equal to F of U plus B minus F of U. Okay, so basically it will be a map. F of U plus B be a map, will be a map in terms of, so that is minus this. So this is a well-defined map from this to this. So this is the definition of linear transformation, affine linear transformation. Okay, so now let's move on to dot products, length and angle in R2. So let us quickly recall. In R2, given two vectors x1, x2, and y1, y2, we define the dot product to be x1, x2, y1, y2. The length of any vector is defined to be x1 square plus x2 square root of that, and the angle was given by the cos inverse of the dot product of vector x and y divided by their number.
Sir, dot product is x1 y1 plus x2 y2.
Sorry, x1 y1, x2 y2. Yeah. Okay. So we can generalize this in Rn, and the generalization is quite the direct one. Suppose you have x1, x2 up to some xn, and y1, y2 up to yn. Then the multiplication dot product is given by xi by I varying from 1 to 2. Similarly, the norm of vector x is defined by the square of all the coordinates and then taking the square root. Okay. And the angle is again the same. It is taking the dot product and then divided by the norm of the visual units. Okay, the similar thing we can do by defining a structure which is called inner product on a vector space, and then we can mimic whatever we did in the case of R2 or Rn in any general vector space. So suppose you have a vector space where addition plus denotes the addition and dot denotes the scalar multiplication over R. So we define an inner product as a function on V cross V to R, satisfying the following properties. Inner product if it is linear in the first coordinate. V1. First of all, it is if it is 0. It is always positive, and it is 0 if and only if the vector is 0 itself. The second case, it is linear in the first coordinate. Third is, yeah, it is symmetric also. So first two conditions, so let me combine these two things. It is linearity in the first coordinate means of both of the things. And then the third condition, it is symmetric, so you will get the linearity in the second coordinate as well because of the symmetric behavior. All right. So any function satisfying any function on the product, on the Cartesian product of the vector space, which is a real value function, satisfying this property is a inner product space. So for example, on Rn, dot product plays the role of inner product. Okay, dot product is one example of inner product. Another example that I gave during my lectures or my live sessions, taking the polynomial space of vector n over x, I define the inner product between two polynomials to be product of their, to be the integral of their product, and the integral over 0 to 1. So this defines a value. This is a well-defined inner product. In case of matrix spaces M2 cross 2, one can define the inner product to be the same as the dot product, the usual one. Or yeah, that's so something like Aij, Bij, sum over. Okay. So there are quick examples. You can figure it out. Nothing new about it. Okay, so now orthogonality. So once you have the inner product structure, you can talk about length and angle. But in order to talk about length and angle, you need norm. So what is the norm on a vector space? Norm of a vector space or vector space. Okay. B plus dot. So norm is defined to be again a function from B cross B to R. Sorry, B to R. Is satisfying these properties. First property is that it satisfies the triangle inequality. Second property, you can take the scalar out with a modulus because we always want it to be positive. So and it is 0 if and only if B is 0. All right. In case of norm in an IPS, what is IPS? IPS is a vector space with inner product structure on it. So norm in an IPS, B comma this norm of B is defined to be the square root of the inner product.
So this is the length also, na?
Yeah, this is the length. Thanks for pointing that out.
Provide some example.
Provide example of what? This norm.
So inner product.
Inner product, I've given example, right? Here, dot product is an inner product. Polynomial space M2 cross M2. I cannot go into detail of this because of the time constraint. Finish off. Okay. I hope I will have some example below. I will discuss them. Okay. So now what about orthogonal matrices? So once you have the norm with the inner product structure, you can talk about the, in some sense the angles. Okay, so we say the perpendicularity concept in R2 translates into an orthogonality. Okay, in case of the abstract vector space. So we say V and W in an inner product space B. Okay, we say V and W in B with inner product are orthogonal if their inner product is 0. Okay, two vectors in an inner product space are said to be orthogonal if their inner product is 0.
So should it be inner product or dot product?
No, I'm working with abstract space. I'm working with inner product space. So in an inner product space, there is inner product. Dot product is a specific case of inner product when I'm working with R. There
So
can be other.
In exam, in the question, if they say the standard inner product, we can assume it's a dot product, right?
If they say a standard inner product or dot product or the space is given to be R3, you can freely work with dot product.
Otherwise, they will specify how the inner product
Exactly.
must be computed.
Exactly.
Okay.
Right. It will be clear from the question. All right. Now, a collection of vectors v1 up to vn, or let's say vk, in your inner product space is said to be an orthogonal subset if vi vj, the inner product of vi vj is 0 for all I not equal to j and varying between 1 to 2. Okay, so if they are mutually orthogonal to each other, then we say the subset is orthogonal. Okay, and whenever you have an orthogonal subset, you can form an orthogonal orthonormal subset. So what is an orthonormal subset? It is a collection of vectors in B satisfying following. First is that V1 to Vk is an orthogonal subset. Okay. The second property is that each norm of each vector is 1. All right. Such subsets of V are called the orthonormal subsets. All right. Now let's look at this question. We need to choose all the correct options. So the vectors in an orthonormal sets are linearly independent. The set of linearly dependent vectors can be orthonormal. A set of linearly independent vectors is always orthonormal. So can anyone tell you what are the correct options?
The first one is correct.
First one is correct, right? Second one has to be wrong, right?
Yeah.
Linearly independent vectors are always orthonormal. No. This is also wrong.
Norm need to be. Okay.
Yeah. Set of linearly independent vectors is always orthogonal, but not orthonormal. Is that correct?
Not always, so it's wrong.
Yeah. Yeah. The vectors in orthogonal set are linearly dependent. That is true. So these two options are good. All right. Now let's talk about projections. So projections are helpful in R2 to calculate the minimum distances between 2 points. Okay. So let me give an example. So we define projections. Let me first define what's the projection. So projection of of a vector v on vector w. Okay, so projection is always onto some vector. Okay, so projection of v onto w, this is the notation, is defined to be inner product of v and w divided by the norm of v square in the direction of w. Sorry, norm of w square in the direction of w. Okay. In case you are working with orthonormal vector or unit vector, if w is unit vector, that is norm of w is 1, the projection of v in the direction of w would be just inner product of w with v in the direction of, okay, because the norm will be. All right, so this is us.
Even if they give not a non-unit vector, we can convert that into a unit vector by taking the norm of that vector, right?
Yeah. So, but then, yeah. So, but it would be same because then you will have w by norm of w here and norm of w here. So
Oh,
but
okay.
you will start the square term, so it won't be matter. It won't matter.
Okay.
So, right. Okay. So, yeah. So, why projections are important? Projections are important in order to find out the minimum distance between a point and a line in R2, or in R3. They are important to find out the minimum between yeah, the same reason, minimum between a point and a subspace. So let me give a quick example. So for example, you are in R2. All right, and there is a line passing. This is the subspace. Okay, this is subspace W, let's say, and then there is a point P. So point P is a vector in R2. All right, so call that vector to be W. So because W subspace also has some unit direction W in it. So if you want to find out the minimum distance between P and this line W, then how do you find out? So the way to find out is to project V onto W. All right. So once you do that, if you project it onto W, you will get something which is going to be like this. And then you know this point, so you will get this vector. Let's call that Q, or let's call that the projection of V onto W. So once you do that, now you have this vector, you have vector V. Now it's a vector calculus. You need to find out this vector. Okay. So what is this vector? This is basically, let's call that point P, O. So now if you look at this triangle, so what is PQ? PQ is OQ minus OP. Okay, you know this vector, this is the projection. You know this vector, this is B. So, and then you can find out the distance, which is going to be the norm. So this will be the shortest distance between P and W. Okay? P and line. All right, now let's look at the question that I have just written. So consider two vectors using the standard operators. Projection of A in the direction of B is given by. So it is very direct question. So it is also an example of the inner product that someone was asking. So let's do that. So projection of A in the direction of B, we need to find out. Now, by the formula is A dot B divided by norm of A, norm of B square in the direction of B. All right. Now, what is A dot B? A dot B, can anyone tell me what is A dot B? A is this, B is this, and it is dot product, so it is direct.
Minus
4,
A dot B is
4, minus 3.
4 minus 6.
It is minus 2
Yep.
divided by what is the norm of B? It is 5. 25.
5.
25.
25. Okay.
And B is 4, 0, minus 3, and that's your answer. Okay, so earlier we saw in this question there was one option which says that set of all linearly independent vectors is always orthogonal, okay, or always but not orthogonal. So this is not true, but one can always convert a set of all independent vectors into an orthogonal vector, into a set of orthogonal vectors. Okay, and how to do that is the process called the Gram-Schmidt process. But before we go into this, let me recall what do we mean by projecting onto set of vectors. Okay, so projection of a vector W in B onto a set of onto an orthogonal set, onto an orthogonal subset. So what do I mean by an orthogonal subset? I'm basically looking at the span of that. Suppose my orthogonal subset is, suppose S is V1 up to Vk is an orthogonal subset. Okay. Now look at the span of this. So now projection of your vector W onto the span of S, it is defined to be projection. So it is defined as projection on each of the vector. Okay, so it is projection on V1, sum of projection on V2, and so on up to projection of W on V2. All right. So this is what is our. So this is called the projection of W onto a subspace.
So here we are taking one vector and then projecting to the whole spanning set of
orthogonal subset. Right. This is how it is defined. Okay, now why Gram-Schmidt process? Gram-Schmidt process, let me write what it does. It is basically a machine. You can think of it as a machine. Let me push this below. So you can think of Gram-Schmidt process as a machine that takes linearly independent set and convert. So it is Gram-Schmidt procedure, and it will give you an orthogonal subset or an orthonormal subset. All right. So this is what it does. And now let's see how do we define it. So let's take this example. Okay, let's take this example and try to convert it using the Gram-Schmidt process. Okay. All right. So we have given an ordered basis B1, B2, B3 of the inner product space. All right. So we have given this B1, B2, B3 of inner product space R3 with respect to a dot product B1, B2, B3. So we have inner product is R3 with dot product. That is that's what given, and then yeah. So the subset is 1, 2, 3, 1, 1, 1, 0, 2, 1. All right. Now we need to find out the orthonormal basis. So yeah. So let's. So it is already given to be B1, B2, B3. So let's keep that notation as well. Okay. So what does Gram-Schmidt process does? So we take the first vector. Okay. We take the first vector itself and keep it as the first orthogonal vector. So let's call E1 to be B1. All right. Now the norm of B is not equal to 1. So So on the left hand side, I will be constructing orthogonal subset. On the left hand side, I will be constructing orthonormal subset. So my orthonormal vector, first orthonormal vector will be V1 divided by norm of V. Okay. Now what is this? This is 1, 2, 3. And what's the scalar? 1 plus 4 plus 9.
Square root of 14.
Square root 14. Yeah. Okay. So E1 is equal to B1. Now what is E2? E2 is you need to take B1. You subtract out the projection of you subtract the projection. Sorry, you take B2. You subtract the projection of B2 in the direction of E1. All right. That is what E2 is. So what is E2? And W2 will be simple. It will be just E2 divided by norm of E1. Sorry, norm of E2. So E2 is simple. So now what is this? B2 is 1, 1, 1. Minus what is the projection? Projection is the dot product. So it is B2 dot E1 divided by norm of
that is
norm
1.
of E1. Norm of E1 is not 1. Norm of W is 0, 1. And then E1. Norm 1 is square, right? This is the projection. So what is 1, 1, 1 minus, now what is B2 E1? B2 E1 is E1 is 1, 2,
0.
yes.
Sir, in W1 we take norm of V1. In E2 we are taking
Okay, let's
norm
take
of E1 square.
Okay, now is it fine? Is it fine?
No, it's about squaring.
Where I have taken the square?
Sir,
This is a projection.
E1 can we take W1 also?
Here we are squaring, right? Norm of E1 is square.
Yeah.
And in
Because,
W1 is equal to E1 by norm of E1.
Yeah, so look at the calculation. There are two different. I'm calculating on the left hand side, I'm calculating orthogonal basis. On the right hand side, I'm calculating orthonormal basis. All right.
Okay.
Yeah. So orthogonal. So E1 is E1 is not an orthogonal. It's not a unit vector. So that's why I'm taking E1.
It's fine if we take W1 also, right?
Yeah, then W1 is also fine, but then I have to project in the direction of W1, which is fine. Okay. It doesn't matter. So, yeah, okay. So if you guys are so confused, so I can take W1, but it won't change my calculations.
Okay.
So now what is B2? What is the dot product of B2 E1? 6. And what is E1 square? E1 square is 14. And what is E1? E1 is 1, 2, 3. Yes, Karthik, you have raised your hand.
Yes, sir. Sir, this E1, E2, somewhere I'm getting, I got lost. If you can just brief what is E1 and what is E2.
Okay.
Even you are considering just as a equivalent to B1 or it's any different?
No. So this is B1, B2, B3. This is B1, B2, B3. Okay, this is your linear independent set.
Yeah.
I'm converting this set into an orthogonal subset on the left hand side and orthonormal subset on the right hand side. All right.
Yeah.
So I start with taking E1 as directly as B1. Okay. But in orthonormal, the norm should be 1. Okay. That's why I divided by E1 with the norm of E1.
So,
right? So this is what your W1.
Just to confirm
now,
my understanding up till this point. So
Yeah.
we are taking the B1, we are directly equating it as E1, which is going to be my orthogonal, an element in the orthogonal set.
Correct.
For orthonormal set, I'm taking the value of E1 or B1, in other words. I'm just finding the unit vector of that by dividing it with the norm, which will give my W1.
Yeah.
Okay. And then when we go to E2,
Yeah, for E2, you remove the projection.
Okay.
You remove the projection of B2 in the direction of E1.
Okay.
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 Yeah. So what you will get? You will get 1 minus 6 by 14, which is going to be 8 by 14. You will get 1 minus 12 by 14, which is going to be 2 by 14. You are going to get 1 minus 18 by 14, which is going to be minus 4 by 14. So it's going to be minus 2 by 7. This is 1 by 7. And this is 4 by 7. Correct? So it will be 7 comes out, 1, 2, 4. And now what will be W2? W2 will be just 1 by 7. Yeah. So square then divided by that. So you get minus 2 by 7. And if you take the norm of this, it will be 1 by 7 will come out, 7 will come on top. And then it will be 4 square, which is 16 plus 1 plus 16 plus 1, 17, and then 4. 21. Square root of 21. 7 7 goes out. It will be square root of 21 on 4. All right. This is your W2. Now for E3, you remove, you start with B3, you remove the projection of
E2.
Yeah, B3 in the direction of E2 and projection of B3. Okay, first in the direction of E1 and then in the direction of E2. All right. So you need to remove projection in the direction, in the both directions. Okay. So now what is B3? B3 was 0 to 1. Projection in the direction of B3. So B3 times E1. So B3 dot E1 divided by norm of E1 square into E1 minus B3 times E2 divided by norm of E2 square in E2. All right. Now what is this? So B3 times E1. So what is B3 times E1? B3 times E1, which is 1, 2, 3. It is 4. 4 plus 3, 7. So this is 7. And E1 square, we already know it is 14. E1, we already know it is 1, 2, 3. So it is 2. So it will be just half 1, 2, 3. All right. Now what is B3 minus E2? B3 dot E2. So B3 is this. E2 is this. Okay. So it is 2 by 7 minus 2 by 7. It is 0. Correct? Yeah, it is 0. So this will be 0. Minus 0. So it is 0. All right. So what we will get after solving this, we get minus half. That's half will come out. So it will be minus 1, 2 minus 1, which is going to be so minus half. 2 minus 1.
1.
1. 1 minus
Half.
2, which is going to be
minus half.
Minus half. All right. So I can take half out and then it will be just minus 1, 2, minus 1. All right. Now, if you calculate W3, it is E3 divided by norm of E3. So what is E3? So E3, norm of E3, it will be just minus 1, 2, minus 1 divided by norm of this. It is going to be 1 plus 4 plus 1. So it is root 6. That is your. Okay. So your orthonormal set and orthogonal set is all there. So E1, E2, E3 is orthogonal set, and W1, W2, W3 is your orthonormal set. All right. Okay. So this is the Gram-Schmidt process for the case of 3 vectors. You can generalize this process for the higher dimensional vectors. So let me, for the higher dimensional collection, for a high dimension collection of vectors. So let me let's say V1 up to Vk is a collection of linearly independent set, dependent subset of subset in V. Then you can define E1, you can take E1 to be V1 or W1 to be E1 norm V1, as we did in the previous case. My E2 will be V1, sorry, my E2 will be V2 minus projection of V2 in the direction minus in the direction of V1. W2 again will be E2 by norm of E2, right? And in general, for J greater than or equal to 2 and smaller than or equal to K, we can define Ek to be Bk minus projection of first with respect to 1 of Vk. Sorry. So Ej will be Bj minus projection of Bj in the direction of E1, projection of Bj in the direction of E2, dot minus projection of Bj in the direction of Ej minus. All right. And my Wj will be defined as Ej divided by the norm of Ej. All right. So define this as this. Then the collection E1 up to Ek is an orthogonal set, and V1 up to Vk is an orthonormal set. All right. So this completes the Gram-Schmidt process in general. Now let's discuss the last topic of week 8. All right. So orthogonal matrices. So a matrix A is said to be orthogonal if A transpose into A is equal to the identity matrix. So it is obviously it is an square matrix, and a square matrix is said to be orthogonal if this happens, or the other way around. Okay. Yeah. Right. And which of the following option is an orthogonal matrix? You can check this condition and you can tell which one is the orthogonal matrix. So, for example, in the case 1, it is an orthogonal matrix 1, 0, 0, minus 1 multiplied with all right. So it is an orthogonal. You can check for this also, other cases as well, similarly. Okay. I'm leaving this as an exercise for you to do. So there is something called orthogonal transformations as well. So let's say B is an inner product. It is defined from one inner product space to another inner product space, where this sign, this symbol denotes the inner product on V, and this symbol denotes the inner product on W. All right. So a linear map from one inner product space V to another inner product space W is said to be an orthogonal transformation if the norm, the inner product of V1, V2 is equal to, in V, is equal to the inner product on the image, on the corresponding image, which is going to be defined in that. Okay.
Sir, along with it, it should follow the conditions of linear transformation also, or not?
Oh, right. I have written the linear transformation. Yes. Yeah, that's added here. A linear map is said to be an orthogonal transformation. Yeah. Thanks for pointing. Okay. All right. We managed to finish the content, which seems to be a lot. Okay. So I hope you have a nice exam, and I revise most of the. I have revised all the concepts, and all the best to you guys.
So may I know how much weightage of questions will be asked between the week 5 to 8?
I don't know.
Okay.
I don't know the answer to that question. Yeah, you may ask Sanidhi whenever he takes the next session. And if there is some well-defined percent weightage to the question, we will announce it someday. But
Hello, sir.
as of now, you can think of it as it is uniform to all.
Okay.
Yeah, there is no special
Sir,
weightage.
sir, where is time available for this session?
Which session?
Sir, of this session PDF, sir.
This PDF.
Yes.
Yeah, I will upload it to the live session notes. I think you guys have access to that. In the sheet, there is a sub sheet where you can find out the live session instructor's notes. I will upload there within half an hour.
Sir, is there any place where I can refer to the solutions of activities or practice or graded assignments? I'm now only getting time to practice them. But when I'm not getting the appropriate answers, it becomes difficult to find out what is the actual answers. Or
So the answers to the questions are available, and
In
for
which-
some of the activity questions, the solutions are already uploaded on the YouTube channel. I'm not sure about you can get solution complete of all the problems, but for some of the problems, they are on the YouTube channel, so you can look.
Okay.
Yeah. Yeah, Rama, you have something to say?
Sir, the last problem that we solved before you started equivalence of matrices. Sir. I just have a very small doubt in it. Sir.
Okay. Before equivalence of matrices.
Yeah,
right?
just before the last problem. Even before this.
Yeah.
Yeah, we were working on the image space of. Sir, here actually the basis of image, we will be taking it from the pivot columns, sir. The original pivot columns. Is that so, sir?
No. The image will lie on. If you take from the pivot column,
Sir, 1 0 0 minus 1 1 0. These are the pivot columns, sir. Here, where you solve the RREF.
1 0 0. No, it's not the pivot, right?
RREF of A, we have this pivots.
So RREF form is this. The pivots
Yeah.
are in the first and the second column.
First and the second column are the pivots, sir. So the original vectors corresponding to these two columns will be this one 1 2 minus 1 and minus 1 1 and 2. Correct, sir?
Okay.
These two vectors will be the column space. So,
yeah, they will be the column space. That is true.
But we have got some other image space, sir. We have solved some other image space. If you scroll down, sir. Scroll up, sir. 1 1 0 and 1 0 1.
Right. Yeah.
No, I can clear the confusion if you allow me, sir.
Yeah, please go ahead.
So basis isn't unique. You can have different
Yeah,
bases
that's true.
in the same space. And Rama, if you go with that method, that you select the two pivot columns, if you solve it, you'll get the same answer.
Okay, so the vectors can be taken from the RRAF also.
Yes. So the 1, 2, -1, -1, 1, -2. If you solve it, you'll get the exact same space, exact same equation.
Yeah. Yeah, we can think of like you can generate these
Take from
columns
RRAF
from
also.
these. For example, let me think. Let's take two in the boards. Yeah, if you take, for example, uh, 2 times 100 and then subtract with this, you will get 2. Sorry, you will get 1, 1, 2, -1. What is this? Yeah, should get 1, 2, -1. Yeah, 1, 2, -1. Correct. Yeah. So this is which is the first column, right? And the second column is again going to be some image of these two things. Yeah, you can basically change bases. So yeah, I missed that point. Thanks for pointing that out. The image of this is nothing but the column space of it. Yeah, that is another thing. Yeah, which you might have seen. Right. So image of P is equal to the column space of A, which I missed. But yeah, this is another method you can use to find out the solution. Thanks, Rahul, for the clarification. Yeah, the bases are not unique, so there can be many choices for bases. Is it clear to Rama?
Yes, sir.
Okay, good.
Thank you, sir.
Oh, no problem. Okay, thank you everyone for your patience and okay. Have a good night.
It's very helpful, sir. Thank you very much.
Thank you, sir. Good night.
Thank you. Good night. Good night, everyone. Thanks. Thank you guys for helping me out during the session as well.
Thanks a
you,
lot.
sir.
Thank you.
Yeah. And sorry for the mistakes.
Oh, no issues. Have a good night.
And good day.